investigate whether the equilibrium can be applied or can be maintained. The block is 500 kilogram. Because it's in metric and I may forget it, I'm going to convert it to Newton very quickly. W is going to be equal to 500 times 9.81, and if you do the math, it's going to be around 9.1 kilo Newton. Then I need to draw free body diagram for this block and show all the forces that act on the block and use the equations of equilibrium to see how much force I need to hold this block on equilibrium. After that, I need to calculate friction, because friction is one of the forces I'm going to show in there, and see whether that friction that we produce is sufficient or not. So this one is 4.1. Then I have another force that is inside this chain, and T, and T is going to have a Y component, which is Ty. I write it. It's going to be T times 4 over 5 based on the triangle that I have here. And it's going to have an X component, Tx. I write that one also in here. Tx is equal to T times 3 over 5. Then normal to the surface of the contact, we are going to have N, and also we have F upwards, that is because of the friction. So this block is tending to move downwards, and two forces are trying to hold it upwards. The two forces are Ty and F. So this distance is 400 and this distance is 600, because this is 600, 800 minus 200. Now we need to write equations of equilibrium and find these three forces. Like I said, then we will use friction to find that friction force, and we will compare it to the magnitude that we need. I start with sigma m. You have noticed that most of the times in examples like this, we start with sigma m because it's easy to find one of the unknowns. And I assume that this is my positive direction. Again, all the time start with an assumption about positive direction. Then point O is this point. I'm showing it in here, also it's here. So it's going to be Ty, which is T times 4 over 5, times the distance is 600, and this is a positive direction. Then minus 4.1 times the distance is 400, and that's going to be equal to 0. Tx, F, and N does not have any moment about this point O. That's why we took moment about point O, and from here we can calculate one of the unknowns, which is T. If you solve this, T is going to be equal to round again 4.1 kilo Newton. That's interesting. It's equal to the weight of carrot. Now this is T. Then if I write sigma fx is 0, sigma fx is 0, I can find n from there. N minus Ty that I calculated, 4.1 times 3 over 5 is equal to 0. That means that n is equal to around 2.45 if you run that kilo Newton. I calculated n as well. And I write sigma f y is 0. Therefore, f plus ty, which is 4.1 times 4 over 5 minus 4.1 is 0. From here, F is equal to 4.1 minus 4.1 times 4 over 5, and that's going to be around 1.64 kilo Newton. So what this says, it means that we need this much friction to hold the box in place. Let's see the maximum force that friction produces is how much. Is it enough or it's not? If it's enough, then our box will remain in equilibrium. Otherwise, it will slide down. So Fs, so this is for checking. So Fs is equal to mu s times n, and that's equal 0.4 times n, which we calculated here. It's 2.45, 2.45, and that's going to be equal to around 0.74 Newton. I'm using red color because it is not sufficient. This is smaller than what we calculated or what we needed. Therefore, it's not enough